Thanks, Bobby, and thanks, Sophie, for inviting me to ADC 2024. It's been a lot of fun to commune with fellow audio nerds for the past 3 days. Sound is so deeply embedded in all of our daily lives. Music and audiobooks and podcasts form the soundtracks of people's daily commutes and workouts. Sound makes us feel the visceral impact of games and in films, and shared sounds and music connect us to one another. Sound can evoke vivid memories. It can bring us to tears, or pull us up out of a depression and get us dancing. And it's people like you working in the trenches of C and C++ and Rust that make it all possible. I think of us as sonic cartographers because we create maps to help other creatives like sound designers and audio engineers and musicians navigate the very abstract space of sound. When did we humans first start using maps? Maps may even predate language. They may even have been part of the motivation for language. Was it fire that made us human, or was it what we did while sitting around that fire? Which I'm going to guess was sharing maps with each other. And by maps, I mean stories. And by stories, I mean songs. Songs about someone setting off on a long journey, detailing the landmarks and hazards and food sources along the way, and returning home to share that information with everyone else. To this day, a lot of storylines for films and books and computer games seem to be about a journey or a quest, basically a map. In her book, Wayfinding, M.R. O'Connor writes that by associating stories with specific places and encoding navigation information within the sequence of songs, Aboriginal people made it easier to recall them through reciting these oral maps. Once we started sharing maps, for the first time, it became possible for us to learn about things that we'd never directly experienced for ourselves. We started on building a collective, distributed intelligence that could extend across space and time and beyond any individual lifespan. And I'm going to guess that our direct ancestors, the 10 times 10 to the third grandparents of software developers, probably took it one step further. I'm guessing they constructed stories about imaginary spaces that didn't exist and events that never happened, basically imagining new regions of the map into being. When you hear the word map, the first thing that may pop into your mind is something like this image from Google Maps, showing the familiar Mercator projection of a 3D sphere onto a 2D image, which preserves the angle between any object and north and ensures that latitude lines are parallel to each other and perpendicular to the longitude lines, making it pretty useful for navigation. But as we all know, these kinds of maps make Greenland look enormous, because the further you go from the equator, the greater the distortion in the distances between latitude lines. A schematic metro map doesn't show you distances, turns, or landmarks. However, it does preserve the order of the stops and the zones, the accessibility, and includes a warning that track maintenance may affect your journey, which is probably the totality of information that a passenger needs to get from point A to point B when you're in a dark underground tunnel without any landmarks and not being able to see the sky. In both examples, the map designer sacrificed some information in favor of preserving what the map maker thought would be the most important information to the users of the map. Well, why not preserve everything? because that would be impossible. A point-to-point map of the universe would have to be as large as the universe itself. And in the end, a map that duplicated the whole universe would not just be impossible, it would be redundant. So a map is not the territory. A map is a way to reason about something in a different domain. Like the way you can use a Mercator projection to reason about your position on a 3D globe. Computer scientist Joseph Goguen wrote, "A user interface can also be considered as a map of the underlying functionality to which it provides access, and that this map should preserve as much structure as possible." Since it's impossible to map everything, Goguen defines the art of interface design as that of preserving the most important elements, connections, and relations, such that sequences of actions and chains of reasoning in the source domain also make sense in the target domain, and vice versa. One of Goggen's design guidelines is that the most important aspects of the underlying model should map to correspondingly important aspects in the interface. That could explain why the continuum fingerboard, for example, doesn't present you with 3 equal dimensions of control. It devotes 1,400 millimeters to pitch, but only 127 millimeters to timbre, and less than 30 or so millimeters to amplitude, which makes sense since the human auditory system is so much more sensitive to small differences in frequency than it is to small differences in amplitude or timbre. Every musical interface reveals a worldview or a way of thinking about sound and music. It affords different possibilities and invites different kinds of actions. Even if we limit our discussion to a single parameter like pitch, the interface can have a big effect on the way you think about pitch, what you can do with pitch, and even on what you might imagine doing with pitch. Mapping pitch to a fader would suggest that pitch is continuous and that you can't get from pitch X to pitch Z without also going through pitch Y and all the other pitches in between. You can't jump instantly between pitches. Mapping pitch to a tablet also suggests that pitch is continuous and that you can also jump instantly from one pitch to another without the intervening pitches if you lift the pen and put it back down. But on the tablet, it's very difficult to maintain a constant pitch, as you could with the fader or with a traditional keyboard. So the software we write, the controllable parameters we choose to present in the interface, and even the relative amounts of screen real estate we allocate to each parameter all have an impact on what kinds of sound and music people will be encouraged to produce with our software. Like whatever new musical scales might be implied by this keyboard imagined by Canva, where the black keys are not arranged in alternating groups of 2 and 3. Jacques Attali summed it up best when he wrote, "Each tool implies an imaginable and explorable universe." When it comes to navigating physical space, people use 2 primary strategies: route or route following, which involves memorizing a series of actions taken at specific decision points, and survey knowledge, which involves understanding the overall layout of a space. For example, like if you were to ask Google Maps for directions on how to walk from Stonehenge to Bristol, it shows one solution that corresponds to a route following strategy. Basically telling you that at a specific landmark, you should either continue, turn left, or turn right, always in relation to your own frame of reference, not the cardinal directions like east and west. People acquire route following knowledge without even having to think about it. But the disadvantage is, if you should encounter a roadblock, you may not have enough information to figure out a detour or a workaround. Google also presents you with an answer based on survey knowledge. The bird's eye view, where locations are relative to a fixed frame of reference, like keeping north at the top. This view uses information like angles, distances, and other geospatial cues to give you an overview of the whole environment. One advantage of survey knowledge is it gives you the ability to come up with shortcuts or to find your way around unexpected barriers. But it does require effortful attention to generate and keep track of this knowledge in your head. It might be worth that effort, however, because people who have survey knowledge rarely get lost. And this is all in your head, by the way, not on your phone. When you step outside later, you may be mapping landmarks in Bristol to place cell neurons in your hippocampus. And you may be computing distances using grid cells in your entorhinal cortex. We can also use these strategies to navigate more abstract spaces. For example, if you have a client or customer under a deadline to process hundreds or thousands of audio clips with your plugin or other tools, for them, it makes sense to follow a route following strategy, step-by-step sequence of instructions that are known to be efficient and repeatable. But to actually create those tools, you, the audio developer, are called upon to find new routes and new shortcuts to increase efficiency or improve sound quality. For that, we're probably employing something closer to survey knowledge, generating a bird's eye view that incorporates knowledge of the entire field, signal processing, psychoacoustics, algorithms, the features and limitations of various different platforms. So we have route following and survey knowledge strategies to find our way through known territories. Now, imagine a space that is so abstract and so unknown that you can't develop complete survey knowledge. You can't even tell the full extent of the space, almost like a dense fog or a cloud. Let's call this kind of space a coordinate-free landscape of unknown dimension, or cloud for short. No relation to AWS. Is there a third strategy for navigating this kind of landscape? A potentially infinite universe where it's impossible to even survey the whole space. Maybe a third strategy could be to take a constructive approach, like the Aboriginal rainbow serpent who explored the empty universe by creating it, by carving out geographical features and naming each one. We could call this third strategy exploration by construction. We can't generate the entire space because that would take infinite time and resources. So we need a game plan for how to start exploring. For that, we could take a cue from nature. Foraging insects appear to take a recursive approach to constructing a map of an unknown space. You can see that the honeybee started from the upper left and took a short round trip in each direction before building on one of the short trips to construct a longer round trip. A similar recursive process occurs at the molecular level. Assembly theory is a somewhat contentious hypothesis advanced by an astrobiologist, Sarah Walker at ASU, and a chemist, Lee Cronin at the University of Glasgow, suggesting that life on Earth could have emerged through a series of self-assembling chemical reactions. Assembly theory provides a framework for understanding how complex systems are built from simpler components through a process of recursive construction. Since each step relies on the results of previous steps, each object, in this case each molecule, contains the history of its formation. It's the pathway by which it could have been built from elementary building blocks using only recursive operations. To explore the contingent assembly space of an object, you break it down into its constituent elementary building blocks, recursively recombine these subassemblies to form new structures, and at each step, you add the new structure back to the assembly pool, so it could be reused in future assemblies. Kind of like the way new ideas and breakthroughs rely on previous ideas and infrastructure having been put into place first. For example, Jeff Hinton couldn't have reignited interest in deep neural nets if Fei-Fei Li, her students, and the anonymous Mechanical Turk crowd workers hadn't created ImageNet first. Systems biologist Uri Alon also talks about an abstract space called the cloud, which lies at the boundary between the known and the unknown. And no, that isn't a coincidence. I went through a lot of contortions to come up with an acronym to fit his terminology. Uri says that in science, and I would argue also in software development, and in music composition and every creative endeavor, we do something quite heroic. Every day, we try to bring ourselves to the boundary between the known and the unknown and face the cloud. Heroic because the cloud can be a scary and uncomfortable place. As Alon found out firsthand when he got stuck in the cloud during his PhD research. Everything he was trying led to a dead end. His experiments weren't working. He started doubting his basic assumptions. He stopped shaving. He could hardly drag himself out of bed. He felt unworthy even to come onto the campus. As he described it, I felt like a pilot flying through the mist, and I lost all sense of direction. He was almost at the point of giving up on his degree when, from an unexpected source, he learned a technique for continuing to explore even when stuck in the cloud. So he did complete his dissertation, and now he has a lab with his own students at the Weizmann Institute of Science. The unexpected source of inspiration was an improv theater group that Uri had joined earlier in the year. Alon recognized a parallel between research and improvisation. In improv, you have to face the unknown. When you create a scene or music on stage without a director, without a script or a score, without knowing what the other characters or players are going to do. The difference was that in improvisational theater, they warn you from day one what's going to happen when you get on stage, which is you're going to fail miserably, and you are going to get stuck. However, unlike his scientific mentors, the improv group taught him some techniques for staying creative, even when stuck in the cloud. One of those techniques, which he uses with his own students now, is an improvisation game called Yes and. In the Yes and game, when someone makes a statement, no one is allowed to shoot it down. You have to accept that statement and build on it by saying yes and ... which ends up to be a recursive, hierarchical way to explore an unknown space by constructing more complex ideas from simpler building blocks and recombining the complex ideas to construct even more complex ideas. At one point, Alon and his students had been stuck in the cloud for a whole year when they were trying to understand the biochemical networks inside E. coli cells. So they admitted, we are deeply in the cloud. So they decided to try the yes and game. One student said, let's just draw this on a piece of paper, this network. And Uri thought to himself, well, we've tried that so many times and it doesn't work. But that's against the rules of this game. So instead, he had to say, yes, and let's use a very big piece of paper. And then another student said, yes, and let's use a gigantic blueprint kind of paper. I know where I could get it printed. And when they printed it out and looked at it, that's when they made their most important scientific discovery. That this complicated network was made up out of a handful of simple, modular, repeating interaction patterns, which reminded them of the repeating motifs in the stained glass window, so they called them network motifs. Elementary circuits that can be recursively recombined to form more complex networks. That breakthrough gave them a way to understand the logic of the way all cells, including the cells in our own bodies, make decisions. By exploring the cloud using the constructive recursive yes and game, Uri and his students had discovered that the biochemical networks themselves are also constructive and recursive. In his book, The Singing Neanderthals, Stephen Mithen poses a question. If our brains are made up of specialized modules that evolved in answer to selective pressures from hundreds of thousands of years ago, how can you explain your ability to use an iPhone and write audio software? Challenges that didn't exist 35 to 100,000 years ago, at least as far as we know. Mithen theorizes that this could only be accomplished through the repurposing and recombination of domain-specific modules, a strategy he calls cognitive fluidity. And there are some studies in cognitive neuroscience suggesting that parts of the brain initially adapted for spatial navigation can be co-opted to perform a broader range of cognitive functions, including memory, imagination, prediction, and simulation. Almost as if we are able to repurpose our navigational brains to do more abstract reasoning about sequences of events. You're probably familiar with Eleanor Maguire's study of London cab drivers, in which she found that the hippocampus of drivers who passed the knowledge test was significantly larger than in those of control subjects, and that the size of the hippocampus was positively correlated with the years of experience as a taxi driver. 12 years later, Tim Griffith's auditory cognition group found a similar increase in the size of the hippocampus of experienced piano tuners, suggesting that the skilled exploration of complex soundscapes may make use of some of the same neural architecture as is used for navigating physical space. An example of the kind of cognitive fluidity that Mithen predicted. In 2006, Maguire and her graduate student, Demis Hassabis at University College London, were doing fMRI studies of patients who had hippocampal amnesia, and they noticed something unexpected. Sadly, not only did people with a damaged hippocampus find it difficult to recall prior experiences, they also found it difficult to imagine new experiences. Further studies by the group led them to believe that the recollection of past experience is actually a constructive process, that memories are not so much retrieved whole as they are recreated out of component parts. In other words, complex scenes, whether remembered or imagined, are constructed of smaller elements that can be reused in several scenes, similar to the way the complex molecules can be constructed using simpler components in assembly theory. Demis Hassabis has since finished his PhD and gone on to co-found DeepMind and Isomorphic Labs. And he also changed his name to Sir Demis Hassabis. In October, I had to edit the slide again because he won a Nobel Prize for predicting the folded structure of proteins using DeepMind's AlphaFold. Hasabi's now views the mind as a simulation engine, writing, in humans, the use of this constructive process goes far beyond simply predicting the future to the general evaluation of fitness for purpose. For example, a scriptwriter writing a passage in a film may play out the whole scene using their construction system, not with the idea of predicting the future, but instead for the purpose of evaluating its aesthetic suitability. So as an audio developer, you may be using your construction system to construct and play out the scenarios of how your application is going to behave and how future users are going to interact with your software. In other words, the best way to predict the future is to create it, which is exactly what software developers do. Software developers go beyond just imagining worlds that don't exist. You actually make them exist for real in the actual physical world. Just by manipulating symbols, you can make a mechanical arm move. You can print a 3D object. You can generate a sound pressure wave that people can actually feel and hear. In a way, software is a kind of miraculous map. At this point, you may be asking yourself, what does all this have to do with audio software? I'll show some examples in Kyma because that's what I'm familiar with, but I think you'll easily see parallels to your own work. So, once upon a time, when I was studying music composition at the University of Illinois, I used to love performing new music for the harp, cutting and splicing magnetic tape, and working with a voltage-controlled Buchla 200 in the experimental music studios. In the terms of Jacques Attali, each instrument implies an imaginable and explorable universe of sound. The harp afforded visceral, interactive control with immediate tactile and sound feedback. Although the diatonic strings suggest that pitch is discretized to scales, and it takes a lot of fancy footwork even to get to chromatic scales. In the universe defined by the analog synth, pitch was continuous. You could interact with physical faders and potentiometers and immediately hear the result. And there was this intriguing concept of voltage control. Signals that weren't audible except in the way that they modulate the audible signal. But the physical process of connecting modules with patch cords didn't encourage quick patch changing, nor was it easy to remember or restore a patch that you'd created in the past. Cutting and splicing tape afforded an unprecedented control over time. With the tape, you could literally hold sound in your hands, and you could rearrange time in the way that a film editor can rearrange scenes and time. On the other hand, it would be awkward, I think, to rearrange and interact with sound in real time on stage in this way. So what I really craved was to be able to combine the best parts of these experiences with the algorithmic structure building possibilities of software. But when I started using the music N type computer music languages of that time, I was disappointed and frustrated for a couple of reasons. First is that they were based on models of music notation played by instruments. That's a familiar model for a harpist, but my experiences in the electronic music studio had given me a glimpse of a radically new form of music. Music that was based directly on sounds, without this intermediary of scores played by instruments. A second source of disappointment was that they were not at all interactive or live in the way that voltage-controlled synths and harps could be. In fact, at that time, it was extremely non-interactive. We would run Music 360 batch jobs on a campus mainframe and schedule once-a-week appointments to use a shared D to A converter. It's like Atali said, each tool, including each computer music language, implies an imaginable and explorable universe. Music and languages imply a familiar universe where music is created by people playing instruments and reading music notation. It's not impossible to use these languages to create more abstract, new kinds of hierarchical sound structures, but it requires working around the model rather than working with their model. I guess I was kind of greedy because I wanted to use software to create music that included live processing on audio inputs, samples, synthesis, and interactive controls. I wanted to make music that was based on sounds rather than notes. And I wanted to be able to perform with it live on stage. It was beginning to dawn on me that if I was going to be that greedy, I was going to have to learn to make my own tools. That's why when Lippold-Haken offered me a research assistantship with the Searle Sound Group in the School of Engineering, I jumped at the chance to go back to school and get a degree in computer science. Lippold assigned me the task of writing software for the Platypus, which was a programmable digital signal processor that Lippold had designed with Kurt Hebel. Unlike their previous digital synthesizers, the Platypus did not have dedicated domain-specific modules like digital oscillators, digital filters, and digital envelope generators. It was more like a blank slate. It had an ALU in the form of 3 multiply accumulators, some registers, sample memory, and a program memory, which meant that the architecture was defined in software. It could do however many oscillators or filters or whatever else you wanted it to be. You could change it to be an entirely different architecture simply by loading a new microcode. For a bit of context, all of this happened prior to the release of the first Motorola 56,000 DSP chip. The 56,000 was released in 1986, and that was 2 years after Lippold and Kurt had built the first Platypus. A program for the Platypus was a sequence of 80-bit wide instructions. So you could do multiple operations in parallel on each instruction. In this snippet of assembly language for wavetable lookup, you can see that the highlighted instruction computes a product, loads the low and high halves of an increment, and computes an add, all in one instruction. The first piece that I did with the Platypus was called Sun Surge Automata, based on the self-organizing 1D cellular automata described in Stephen Wolfram's book, and a quote from Lewis Thomas about how energy surging from the sun fuels the transformation of inanimate matter on Earth into the improbable ordered dance we call life. So I wrote an assembly language program to generate a rhythmic pattern of clicks using Rule 90 1D cellular automaton, and another program where I used the cellular automaton as a pattern of gates applied in real time to my voice as I was reading the Lewis Thomas text. And yet another program where I apply Rule 90 to an audio signal by computing each output sample as a function of the previous and next samples in a buffer, which ends up to be pretty close to a Karplus-Strong type resonator. I would load one program at a time into the Platypus, and then record and mix the output onto the hard disk system that Kurt had designed. So I was happy. because there were no instruments, no notes. Instead, the structure was self-organizing patterns of clicks and algorithmic signal processing on the live input. With the Platypus, I finally had access to the virtually infinite flexibility of software sound, and I could hear the results in real time. Instead of working with one specific machine, I could create any virtual machine, albeit only one at a time. Which brings to mind what my friend Joel Chatterby used to say about the difference between control and power. He described control as being like when you're in a startup and you do everything from the lowest to the highest level jobs. And power as being like a big shot CEO where you articulate a vision and then you delegate the implementation to other people to work out the details. Although in this case, it's other programs. So at this point, I had a very high degree of control because I could write whatever sequence of machine language instructions that I wanted, but I didn't have a powerful way to leverage that control. There wasn't a mechanism for reusing the microcodes or combining them in new ways, which reminds me of Joel's favorite question to pose to his students, which is, what do you do when you could do anything? It's the sound space equivalent of what you do when you're facing the cloud. And once again, the best strategy may be to explore and map the space through recursive construction. So I set out to design a language that would help a sound designer or composer explore the space of computable sound through recursive construction. And that turned into Kyma. Kyma is like a continuously updated, queryable database of objects, called sounds, that one can recombine in new ways and save back into the pool of available subassemblies, like in assembly theory. The more you use Kyma, the larger the database of custom sounds that you have available for use in constructing or assembling new sounds. A Kyma sound is a directed acyclic graph, a DAG. Basically, it's an abstract syntax tree for a functional language. Sounds are always well-formed. There are never any dangling wires because the metaphor isn't a wiring diagram. It's a function. You modify a sound by replacing subgraphs rather than by dragging modules into a window and hooking them up with wires. Sounds are immutable because they're functions. So each sound contains a trace of its history in the form of the subgraphs used to create it, like the assembly path in assembly theory. Each node in the sound graph has internal parameters, meaning that state and control logic are internal to each function, minimizing external dependencies so sound graphs can be interchangeable. The idea is that any sound, no matter how simple or complex, can be substituted with any other. A parameter value can be a constant, like this number 0.5, or it can be a runtime variable called an event value, like freak jitter, that acts as a placeholder for a live control stream. An event value automatically generates its own widget in a virtual control surface that you can optionally remap to external control sources, like a stream of data collected in a scientific experiment, or generated by a game track or a tablet. Or a parameter can be the signal output of another sound, pasted into this sounds parameter field, the voltage control idea, inspired by the analog synth. For example, an amplitude follower on the live microphone could let you use your voice to control the amplitude of this multi-sample cloud. You can define interactions between internal and external data streams and sound parameters using a functional reactive language called Capitalk. A parameter field can also be set to a compile time variable, like in this case, file names, as a placeholder for a collection of file names, which is bound by an environment sound anywhere to the right of this one in the graph. A sound with variables in its parameter fields describes an assembly space. It represents not just one specific sound, but an explorable space of possible sounds. It's a way of generalizing from one specific function to a family of possible structures. This allows someone using Kyma to manipulate these structures before evaluating them by using something called metasounds, which are sounds that create other sound structures. For example, this is a metasound that takes the top branch, a sound of variables, as a template and generates a new graph that has 4 branches, one for each channel number, each with a different triggering pattern. You could also ask Kyma to explore the space of a sound algorithmically by selecting the sound and asking it to generate a gallery of examples based on that sound. And the sounds constructed in the gallery, like any other sound, can be reused and recombined with other sounds to create more complex sound structures. This is also a sound, but it's presented with a different graphic interface. So in the Kyma timeline, the task at hand is specifying the start times, durations, and simultaneity of sounds, not designing the signal flow of an individual algorithm. So in order to give more screen space to the task at hand, the timeline interface displays each sound as a simple box, rather than as a signal flow graph. It sacrifices some content to make the form, in this case, the timing, more clear. Behind the scenes, a timeline is also a sound. This is the timeline from the previous slide presented as the graph that includes time offset and set duration modules. It's exactly the same object as the timeline. In fact, it's what the timeline turns into when you press play. You could work with it, you could construct it and work with it this way. It's just that this interface doesn't invite you to think in terms of start times and durations in the same way that the timeline interface does. Here's yet another way to interface with the sound graph. The multigrid is an interface for improvising with sound structures. For example, for interactively changing the routing and the scheduling of sound synthesis and processing algorithms without a predetermined sequence or duration. So in this interface, the most important state to control and display is which sound is currently active in each track. And this is the same multigrid displayed as a graph, one with conditional switchers along the paths. Although this interface shows all the same underlying functionality as the multigrid, it doesn't present a very inviting way to imagine performing the structure dynamically in the way that the multigrid does. So the Kyma structure, the Kyma sound structure, was just my attempt to start exploring the abstract and seemingly infinite space of all computable sound. In other words, to explore the audio developer's version of the cloud. Kyma is written in Smalltalk, a language that invites the programmer to think in terms of exploring and mapping the space of possible programs using recursive construction. The Smalltalk environment is like a large database of code modules, objects, that you can recombine and modify and build upon, and anything you add or change becomes part of the language. Because of encapsulation, hiding of state, and the extreme late binding of messages, you can incrementally modify Smalltalk even while it's running. Adele Goldberg's Blue Book provides the entire Smalltalk virtual machine, the Smalltalk interpreter, written in Smalltalk itself. So I think that Smalltalk influenced my thinking, as indeed every programming language has an influence on how you imagine approaching a problem. Because a programming language is also a map, a representation of the underlying functionality to which it provides access, whether that's a virtual machine or assembly language or the hardware. Even though in theory any Turing-complete language should allow you to implement anything, we all know that in practice, some things that are easy to implement in one language can be pretty intimidating to accomplish in another language. So the language you're using can influence what you might choose to do, and even can influence what you might imagine doing. Alan Kay, who was one of the original Smalltalk designers, thinks that people who are really serious about software should make their own hardware, because they really are part of the same thing, and they can evolve together as a system. I think that's why Apple designs their own hardware, and they even have designed their own version of the ARM processor, optimized to make their software look good. When I graduated and started Symbolic Sound with Kurt Hebel, we realized that producing the hand wire-wrapped platypus at scale was impractical. So we had to come up with a new design based on commercially available processors. At that time, the only commercially available DSP was the Motorola 56000, and it was half the speed of the Platypus. So if we wanted to match or exceed the Platypus power, our only choice was to use more than one 56000. Kurt ended up using 8 56000, each one on a plug-in card with its own memory, so it was modular and scalable. The functional nature and modularity of Kyma sounds meant that they could be broken down and scheduled across multiple independent processors automatically in Kyma without requiring user intervention. On the software side, I wrote versions of each of the next sample algorithms in 56000 assembly language. That way, we could use either the Platypus or a capybara. That's a process we've repeated several times since then, each time we switched to a new processor family for the audio processing unit. First, when we moved from the Platypus APU to the capybara. Next, when the capybara APU evolved into a Pacarana. And again, when the Pacarana evolved into the current APU, which is named for an espresso drink. Each generation of the hardware has evolved to evaluate Kyma graphs more efficiently while preserving the same interface between the APU and Smalltalk, meaning that the sounds our customers created using previous incarnations of the hardware continue to work on the newest version, and making it possible for us to support current and previous generations of the hardware with the same Smalltalk code. And when Apple and Microsoft switched to a new operating system or processing family, we can rewrite the Smalltalk virtual machine, the Smalltalk interpreter, without changing Smalltalk or APU code. In other words, it's still a lot of work, but having distributed virtual machines means you don't have to update everything all at one time or rewrite everything from scratch. Because a virtual machine is also a map, an interface to an underlying hardware functionality. The exploration by construction approach afforded by the sound DAG turns out to be a good fit for sound designers who have to quickly explore a rapidly changing landscape of demands, especially when there's a premium placed on novelty, as it often is for game sound, special effects, or creating the voice of an iconic character. It's also a good fit for composer-performers who create synthesis and processing environments for themselves, in which the mode of interaction and combination of algorithms changes multiple times over the course of a performance and has to happen while they're performing and interacting with it live on stage. It was designed for people who have to confront the cloud in their creative work on a regular basis. Speaking of the cloud, when you get home after the conference and start working on something new, I promise you, at some point or another, you too will face Uri Alone's cloud. It's happened to me many times, including several times while I was working on this talk. But actually, the cloud is a desirable place to be because it's an indicator that you might be close to a breakthrough. You might be about to discover or create something truly new. The only problem is when you feel stuck in the cloud and you can't see any way out. When Uri Alone notices one of his students getting stuck in the cloud, he steps in because he knows from experience that if you're feeling fear and despair, your mind narrows down to safe and conservative ways of thinking. And that if you would like to explore the risky paths needed to get out of the cloud, you need other emotions like solidarity, support, hope, that come with your connection from somebody else. Uri says that in science, it's best to walk into the unknown together. I wonder whether the same could be true in the often solitary pursuit of software development. Are there ways for us to play the yes and game with each other? Yes, because that's exactly what's been happening here over the past 3 days. You present your work or work in progress, and someone may come up to you afterward and say, yes, and did you also think about trying this? And you might continue that discussion on Discord even after you get home. And now we can even play the yes and game with every human on Earth throughout human history, by interactively prompting a large language model, where the answers you get are sometimes just as fanciful as you might hear from an improvisational theater group. Because a large language model is like all the stories told around all the campfires over all time. To map the high-dimensional semantic space spanned by all these stories, an LLM also takes an exploration by construction approach. It takes the stories, breaks them down into constituent parts or tokens, represents the tokens as numerical vectors and embeds them in a high-dimensional semantic vector space. Then, through a process of self-attention, recursively recombines these subassemblies to form complex structures in the semantic space that represent the meaning of phrases and sentences and documents and so on. At each step, the new assemblies are added to a pool of available representations, allowing for the construction of increasingly complex semantic structures in order to create a map, an interface to some underlying functionality, which is, in this case, us. It's an interface to the ever-expanding network of human minds. In other words, LLMs aren't intelligent. LLMs are maps to our own collective distributed cognition. As Lewis Thomas wrote 50 years ago, We are becoming a grid, a circuitry around the Earth. The great mass of human minds around the Earth seems to behave like a coherent living system. That's why I was puzzled last year when AI researchers like the Nobel laureates Geoff Hinton and Demis Hassabis warned about an existential risk from AI. Because isn't AI just us? Isn't an LLM just a map of what's really going on, which is the emergence of the next hierarchical level of our own distributed collective intelligence? Fearing those maps is like fearing ourselves. But then again, maybe there are some reasons to fear our collective selves. Or maybe it's just that the interface is just not quite good enough yet. It's not preserving enough of the underlying structure of our collective intelligence. For that, we may have to train them on more than just language. We may have to train them on spatial maps. Fei-Fei Li, the godmother of AI, says that visual spatial intelligence is so fundamental. It's as fundamental as language, possibly more ancient, and more fundamental in certain ways. That's why her startup, World Labs, is training large world models, LLMs, on 3D visual spatial data. But why did she stop at visual spatial intelligence? Probably because she's a computer vision researcher. But spatial intelligence is not just visual, and it's not just about static 3D representations. It's also time-dependent, which is something audio developers have known since forever. It's the dynamics, it's the narrative that carries a lot of the meaning. Training LLMs on dynamic spatial data, including sound, is what's going to unlock the next epoch of artificial intelligence. Do you ever ask yourself, why do you intentionally choose to work on something as challenging as real-time audio computation? I think there is a reason we're driven to do this work. Sound and music are among the most profoundly meaningful of all human communication. And you are the sonic cartographers. You face the cloud every day and use the neurons in your hippocampus and entorhinal cortex to constructively imagine a map through this abstract infinite space. You know how to turn that map into a sequence of symbols, and you know how to map those symbols into reality, bringing to life a physical sound pressure wave that people can actually feel and hear. It's almost miraculous when you stop to think about it. And we're so lucky to be doing this work. Thank you.